This is kinematics and force analysis. So this is KAM and FAM, which is good. Those are special. Anytime you can combine topics like that. Okay, let's do the read through. And this is 618. You testify as an expert witness because once you've taken Physics 211, you qualify to be an expert witness at many trials. And your job is to find the impact speed. So let me read through this. You testify as an expert witness involving an accident in which car A, which for me looks blue. So car A is this blue car. This blue car is cruising down a road. Let me just read through. This blue car slides into car B because why? Car B, which is this green car, is sitting here stopped at a red light. So this is sitting here perfectly motionless. You're driving this blue car, car A, automobile A, object A, and then all of a sudden you see that the green car is sitting there stopped. At this distance, oh wait, you slam on the brakes. So you slam on the brakes when the driver of car A puts the car into a slide, meaning you slam on the brakes because it lacked automatic anti-brake lock system. I think that should be anti-lock brake. But anyway, imagine the terror. You're driving down this ramp. All of a sudden, you see this green car stop there. You slam on the brakes and you crash into the green car. And the question that we have to figure out, what is the impact speed? What is the impact speed between the green car and the blue car? And I'm saying that because this is green and this is blue. What is the impact speed? And then we need that for this case. It's probably an insurance company case. All right. So to me, right away, I'm just thinking kinematics. Number one, this is a job for kinematics. This is a job for kinematics analysis method. KAM. Okay. So you know what that means. There's a whole recipe. Do the recipe, apply the recipe. Just like the force, apply KAM recipe. The KAM recipe means let's label everything. Okay, and you know what else I'm going to do here? I'm going to for the coordinate system, I'm going to play the same coordinate system that I always play. What should I do with my coordinate system? I know this blue car is going to accelerate along the ramp surface. So here's a question. Does this blue car accelerate down the ramp? Is this the direction of acceleration? So again, it's after I slam on the brakes. When I slam on the brakes, does the blue car continue to accelerate down the ramp, or does it accelerate up the ramp? And the answer is, I don't know. So because I don't know, I do know one thing. The acceleration is for sure along the ramp. So because I don't know, I'm just taking a wild guess, and I'm going to call this plus X. For no reason, the one thing I do know, let me just repeat that, is I do know whatever the direction of acceleration is, it is along that, it is in that direction. Maybe it's in the opposite direction, and I'll find out soon enough, I guess. All right, so that is my x-axis. This would be my y-axis, kind of overlapping things. Okay, so I'm good to go as far as that coordinate system is concerned. Now, again, I'm doing the CAM recipe, which will be stipulated on the exam one. Exam one say, hey, solve this problem and make sure you specify every aspect of the CAM recipe. And you have that in your green sheet, so you're good to go there. All right, so what do I need to specify? I need to specify all the kinematics things, and you've seen this before. I'm going to call this X initial. This is going to be X final. That's the point of impact. X initial, I guess I'll just call 0. That's fine. VX initial. So you slam on the brakes. When you slam on the brakes, your car, in my case, my car is going 16 meters per second. 16 meters per second down the ramp. And down the ramp is called plus. So this is for sure a plus. That's good to know. A sub X. A sub X equals, I have no idea. The only thing I know about A sub X is it's going either down the ramp or up the ramp. What else can I say here? VX final. VX final right here. VX final is the dollar sign. So this is my dollar sign, VX final. VX final. That's the dollar sign, the impact with which the blue car strikes the green car. Time is, I don't know, and I might not care. That's it. I've got my coordinate system. I've got my label, all of my kinematics labels up and running. And now the next question is, what do you guys think? Is this, let me move over here in case I'm getting too low on the horizon. Number 4. Here's the next recipe item. Is this constant acceleration kinematics or is this variable acceleration kinematics? If it's variable acceleration kinematics, this is a job for calculus. If it's constant acceleration kinematics, it's a job for the big 5. And you know what? I'm thinking this is constant. This is constant acceleration kinematics because every force acting on the blue car is constant, which sort of begs the questions. What are the forces acting on the blue car? So I'm going to do that here. I'm just going to I'm going to sloppily overlay things because I don't think it's that hard to see. Okay, so ready? Force analysis. So I'm kind of bleeding over into force analysis method. This is the normal force. This is the weight force. And this is the friction force. Because I'm skidding. I'm skidding, so I know for sure I have friction. I got to label this stuff. Not only I'm skidding, I know I have friction, and I know it's kinetic friction. So there's no uncertainty there. The blue car is skidding down the ramp. Kinetic friction always opposes velocity. If the velocity is down the ramp, kinetic friction is up the ramp. This is my normal force, F sub N. This is my weight force, mg. Okay. I guess I have to decompose because I have one 2-dimensional vector. So this is business as usual. This is really probably starting to look pretty familiar to you by now. We've done this so many times. This is mgx. This is mgy. Okay. And this ramp angle theta there is this ramp angle theta here. So I know I'm being I don't know if overlapping all this is such a good idea, but it seems convenient. Hopefully you can read it. All of these forces that you see in this free body diagram, they're all constant. None of them are varying as a function of time or position. So this is constant acceleration kinematics, which means you now use a 6-column data table. Just like always. All right, so X initial, X final, VX initial, VX final, A sub X, and T. And now it's just a game. What do I know as far as these entries are concerned? X initial is 0. X final is D. So for me, this is 23 meters. This is given. D equals 23 meters for me. My initial X velocity is down the ramp, so that is a positive number. And as mentioned, it is 16 meters per second. This is my impact velocity, VXF. This is I don't know and I don't know. So for number 8, I'm going to write, uh-oh, uh-oh, too many unknowns, too many unknowns. But you're not going to panic. And how do I know there are too many unknowns? Because if I just say, well, I don't know time, I don't know acceleration, I don't know final velocity. That's too many unknowns. So now what is the question? Number 9, now what? And a knee-jerk reaction is, for me at least, look at a Y force inventory. Or no, not look at Y data. But I don't think that's going to help me. I don't think looking at the Y data is going to help me as far as finding out any one of these variables. It's just because this is why the Y data, there's nothing happening in that dimension that I can see any connection with the final x velocity, a sub x or t. Okay, so unlike projectile, this is not 2D projectile motion. In that case, you could find something from the Y data. So I'm going to look at Y data. No. Look at force analysis. Look at FAM. All right, so if I look at FAM, and I know FAM is all about just cranking out F equal MA equations over and over again. And there's A. So, I mean, acceleration is sitting right there in Newton's second law. So that's the path I'm going to go down. All right, so I'm going to say my X force inventory looks like this. Sum of all those X forces acting on the blue car. And this is where your free body diagram needs to be very accurate and complete. I've got MGX pulling the car down the ramp. Yes, I do. Is that it? I suppose. And then I got kinetic friction trying to stop that downward motion equals MAX. The next thing you have to do is say something about acceleration. And there is something to say about acceleration. A sub X, in this case, is the $sign. So that's good news because if I process this, if I process my X force inventory, I've got MGX, which is mg sine theta, yes, minus FK, which is mu sub K F sub N, equals MAX. What's F sub N? So this really does look pretty familiar. You hopefully are starting to see like repetition. What's F sub N? Well, if I do sum of all Y forces, I have F sub N going up, and then down I have MGY equals MAY. Say something about acceleration. A sub Y equals 0 since there is no plus or minus Y motion. In other words, the blue car stays on the ramp. Okay, so for the umpteenth time, you're saying, yes, I get it, I get it, I get it. F sub N equals mg cos theta. Okay, so that should really be pretty straightforward at this point. All right, so now let's update number 13. Update number 13. This is what I have now. Here's my new and improved number 13. Mg sine theta minus mu sub k mg cos theta equals MAX. And there's my answer to acceleration. My acceleration is A sub X equals mg sine theta minus mu sub k mg cos theta all over m. And you can see some cancellation. So this gets simplified. M cancels, M cancels, M cancels. I'm going to get a number on that, and I'm going to keep this number and store in calculator memory location A. All right, so let's get a number on that, and then it's back to kinematics. G, 9.8 times sine of 14 minus mu sub k, which is 0.58. It's a dry road, times 9.8 times cosine of 14. I get this. Ooh, I get a negative number. That's very interesting. This equals negative 3.144 meters per second squared. And that's sitting here again in memory location A. Store alpha A. And let me just redo that a second time just to double check. 9.8 times sine of 14 minus mu sub k, which is 0.58 times 9.8 times cosine of 14 degrees. All right, I'm getting the same answer twice. So note, that negative sign is pretty interesting. Number 19, aha. Blue car, mass A, blue car, blue automobile. The blue automobile accelerates up the ramp. Blue automobile accelerates up the ramp. So the blue automobile is moving down the ramp, but it's accelerating up the ramp. Isn't that interesting? Let me say that again. Yes, for sure. You slam on the brakes and you are moving down the ramp. But as you move down the ramp, as you're moving down the ramp here, you're slowing down. And so if this is your velocity vector, your acceleration vector is up the ramp, and that means slowing down. You're moving down the ramp, but you're slowing down as you move down the ramp. Number 20, let me go over here. Back to kinematics. Okay, so back to number 7. Update number 7. Here's the new number 7. Number 7 was my table. So this now, instead of question mark, this is calculator memory location A. I have that. I figured out that number thanks to force analysis. So I'm going to play the Big Five game. If I now play the Big Five game, and the Big Five game says, which Big Five equation contains the variable you care about, contains the $ variable with all other variables known? And in this case, I'm going to guess this. VXF squared equals VXI squared plus 2A sub X, X final minus X initial. Okay. So before I keep going here, VXF, well, this is the $, so it's okay that that's unknown. Do I know VX initial? Yes, I do. It's sitting there in my data table. Do I know acceleration? Yes, and don't forget the negative sign. Do I know X final? Yes, it's in my data table. I know everything here. So go ahead and solve for the impact velocity. 22. But they don't want velocity, they want speed. So remember, speed, we know the velocity is down the ramp, but they don't care about direction. So just speed equals the absolute value of velocity. And if I do this, let's see, let's get an answer. 16 squared plus 2 times alpha A times 23 square root. Okay, 10.55. This is my speed, 10.55 meters per second. That is the answer to part A, thanks in large part to kinematics analysis method and force analysis method. Now, what I'm going to do, let's see, let me do a time check here. It's now 3:24. Here's what you guys can do for part B. Part B is identical. Part B is identical to part A, except there's wet leaves on the pavement. So things are slipperier. So for part B, everything's the same, except instead of the coefficient of kinetic friction equaling, in my case, 0.5, mu sub k now equals something less, for me, 0.17, because it's slipperier. Wet leaves are slippery. So now much more dangerous, much more sliding. Leaves are slippery. So go ahead, repeat everything. Let me scroll down a little. Well, let me zoom out. You can repeat all of this, and it's going to go quickly. You can repeat all of this for this new coefficient of kinetic friction. And I'll just write that down, number 24. Repeat steps. Everything's the same. I'm just going to say repeat with mu sub k equals 0.17. Okay.